And today we are going to look at the gyroscope, but first of all, I would like to indeed give you some further details about the star triggers, because yesterday there was one question regarding one configuration that it was found in literature, and one of the main concern regarding this question was indeed why the star triggers of the Hubble Space Telescopes are pointing on one direction. And during my lecture, I said that if you want to determine the attitude of a spacecraft, you want to have, for example, two star triggers that are going to point at two different regions of the sky, because you want to have at least, so you want to determine the attitude in the triaxial reference frame. So you want to have the correct determination of the attitude for example, a three-dimensional stabilized spacecraft. As I said yesterday, the telescope, as we also have seen for a laser altimeter, represent a payload with different requirements. And the main requirement indeed for a telescope is that you want to point a specific region of the sky, because that represents your main goal. So, as I said yesterday, when you are pointing, so the telescope, so the payload itself can be very similar, can be associated to the star triggers, because indeed they are, so the telescope is going to look at the sky, and so it's going to use the stars not to determine the attitude of the spacecraft, but to accomplish some scientific objectives. But basically, the principle of a telescope is really similar to the star trigger. So the reason why those star triggers are aligned and basically are pointing in a way to determine the attitude of the spacecraft that enables a precise pointing of the telescope, is because basically, if you look at this figure here, the axis, the bore side of the telescope is this one. As I said yesterday, when you are going to point a star trigger in this direction, the precision that you have for the orientation of the spacecraft along this axis is the less accurate if you have a star trigger pointing towards this direction. So what you want to determine is indeed, so basically what did happen for a telescope is that you're going to have your image rotate along this bore side direction. The main goal of a telescope, for example, in this case, for the Hubble Space Telescope, is to determine the precise attitude with respect to the two orthogonal axes, this one and this one. So if you have rotation along this axis, what you have is that the bore side of the telescope is going to point different region of the sky. So the requirement on these two axes are really important. That's the reason why so the position of the star trigger is indeed aligned to the position of the telescope, because as we said, the orthogonal, so the axes that are orthogonal to the bore side of the star trigger are basically the axes that you can determine with a more accurate precision. So if you have a star trigger that is pointing to the telescope, so in the direction of the telescope, you are able to determine the orientation of the telescope in these two axes with a very high precision, as we saw yesterday. So at the level of milliarc seconds, if you want a very precise star trigger. Well, this is very similar to what we have seen at the beginning of the course, this part of the course, when we have seen the laser, the LiDAR, so the laser altimeter. Same idea here. As I said, the detector of a laser altimeter is indeed a telescope. So you have a star tracker that is pointing towards the sky in order to determine the attitude of the telescope really precise. Basically, you don't care that these rotation, so this axis is not really well determined, because if the telescope indeed is rotated, the laser altimeter measurement is not really affected, because it usually has this sort of a circular pattern. So you're not basically seeing any differences if you have rotations of the telescope in this direction. On the other hand, you need to have a very high precision of the attitude in the orthogonal direction, because if you have, so in this case, a roll axis angle or a pitch angle, what happened here is that the telescope is not pointing, nadir pointing, and you are going to have a significant error in your measurements. So the telescope and the laser altimeter itself represents indeed a very basically a very particular case, because you need to you have very stringent requirements along these axes. When you have a 3D stabilized spacecraft, what you need to have is indeed an equal accuracy in all the three axes. So that's the reason why you need to have that the star trackers are going to point at two different regions of the sky. And if you want to have redundancy, you can have a third star tracker. So the other question that I got today, actually there was another one regarding that I received by email about the aberration. So I tried to re-explain briefly both errors. So we have seen briefly the errors related to the measurement given by the sensor, and the so the W, the error in W, and the error given by the star catalog. So the error that we called in the unit vector V. So the vector error V is given by the proper motion of the star, as we have seen, because stars are at different distances. So you can have that the velocity of one star that is closer to us, can be basically seen in a different, with a different distance to other stars at the background. There are basically at the very farthest part of the universe. The other important error can be given by the stellar parallax. So if you are in a different, so assuming that you are on the Earth and you're observing a star, when you are at different region of, so at different parts of the Earth's orbit, you're going to see one star that is closer to us, so a near star with respect to the background, at a different proportion, so at a different projection with respect to the background stars. So if you are here, you can see that this stars is projecting in this part. If you are in this other side of, so these are a little bit of course emphasized, but if you can see here, if you are here, basically the same stars appear to be at the left side with respect to this one. So this is the stellar parallax that is not associated to the motion of the planet, but only to the relative position of the planet in its orbit. The aberration is related to the velocity of the object. So also the Earth is affected by aberration because it's moving around its orbit. But it's only its velocity that affects the aberration. So basically, assuming that So you know that the Earth is moving with the velocity, relative velocity to the sun that is high, and it is indeed sometimes a few tenths of a kilometer per second around the sun. You're able to see aberration effect due to the fact that the Earth is moving in with respect to the sun. And so in the inertial reference frame, you are observing stars with an upper position that is given by the velocity of the observer. So the Earth is moving, and so you're seeing these objects at a different distance. So at a different part of the sky. So you think that the object is here, but this apparent position is given by the fact that the Earth is moving. The other table that I show you is related indeed to the measurement errors. I know that these tables are not really clear, but are referred to basically a very realistic star tracker that show you the errors that you have in your star sensors related to the magnitude of the stars. So basically at different magnitude, you have that the error sources are slightly different. So that's the reason why you have one column that show you the magnitude. The differences between these two tables is related to the position of the star and the magnitude error. So if you have an error in the location of the stars in your CCD, so in the first table, you have that for stars with the 3.0 apparent magnitude, you can have an error for that particular star tracker of about 1.23 arc seconds in the row axis. Row axis means when you look at the CCD, this is the row axis and this is the column axis. It's like the matricial form. So this, since the CCD is a matrix, means that you for those stars you can have an error of 1.23 arc seconds in position. So basically the mismodeling of the pixels can give you this error. For the column you have 1.28 arc seconds. Those are the effective errors. What is reported in the third column is the requirement. So when you design an instrument, what you have to do is to provide some requirements, and the company that is going to develop the instrument, to design the instrument, is going to satisfy the requirement that you have chosen. So usually the requirements are given by the operation of the spacecraft. So if you have a specific instrumentation on board for telecommunication or other duties, those instruments give you the upper bound of the requirement. So basically, at least you have to reconstruct the attitude with those requirements, with those accuracies. These columns show you that basically for that particular instrument, you are satisfying the requirements within actually basically a factor of 3. So those that means that your instrument works properly. The first column give you also the different error types, because the first part give you the errors associated to a bias. So basically a bias to your measurement. The second row is related to static random noise. So basically the possibility to have not only a bias in your measurement, but also a noise that could be modeled with a Gaussian random noise. So basically a normal distribution. So if you have, if you want to write in a statistical point of view, usually what you have is that if you have a zero bias measurement, you have a Gaussian distribution, you have something like that, right? Your sigma, that is the sigma reported here. This one, these two values give you the offset of this. So basically a bias in your Gaussian distribution, okay? And this is only related to the position, location of the stars in your CCD. So that means that you are trying to determine, so that your CCD is affected by these errors. So are errors associated to the technology of your instrument, so your CCD. The other source of error that you have is related to the filter, because as we said, when you want to determine a star, you have to take into account that since you can have in your field of view different stars, in order to avoid ambiguity, you are trying to select the stars that are really in that basically provide you a better signal. So usually you constrain your stars to be, for example, with the magnitude of 3 or 5. In order to be able to determine the stars that you need, you can have also an error in the magnitude. So when you want to determine if a star is within that level, that range type, with that range of magnitude, you can have an error of 0.12. An example that I did yesterday is indeed, if you have a star that has a magnitude of 2.8 and the other one is 4, so basically, sorry, if you have 2.8 and you have 3, you are able to distinguish between the two stars, because the errors is 0.12. If you have a stars with the magnitude, the difference less than 0.12. So for example, if you have 2.98 and you have 3 magnitude, that seems a small number, but as I told you, the magnitude is a logarithmic scale, so it is a large difference between the two stars. You're not able probably to distinguish between the two stars. So that measurements give you the basically the possible criterion to select the stars. So if you want to be sure that your stars can be distinguished between the others, you need to have, for example, take into account this difference in the magnitude. The requirements are always larger than the measured error. And also for the magnitude of the stars, you have a bias, as I wrote here, and a 3 sigma repetitivity. So this is a sigma, 3 sigma accounts for the 97% of the errors. Okay, so that actually concludes the part on the star trackers. So during the break, if you have questions, we can still discuss about that. But yesterday, we started to talk about the laser gyroscopes. Laser gyroscopes, so we already introduced yesterday the fact that we don't need to, so in space, mechanical gyroscopes are not really used. And for example, several years ago, the main gyroscopes that were used were indeed based on mechanical parts. So basically you had a rotor with high speed, and the measurement of, so the conservation of the angular momentum of this wheel, of this rotor, basically represented the principle to measure the inertia, so the angular velocity variation with respect to the inertial reference frame. Those gyroscopes are not used for many reasons. First of all, because you want to avoid mechanical parts with rotating, with movable parts. And second, because are really affected by long-term instability. And so that in space will be really detrimental, because what you want to avoid in space is that after 1 or 2 years, your instrument is completely useless. So laser gyroscopes represent a very concrete technology that is used in space. The other gyroscope that we're going to see today, it is called hemispherical resonating gyroscope. So the hemispherical resonating gyroscopes are mechanical in the sense that they are not going to, so you are not going to use the Sagnac effect that we have introduced yesterday, but relies on the mechanical properties of resonators. So what we are going to see that there is another family of gyroscopes that is mechanical gyroscope, but without any movable parts. So let's start with the laser gyroscopes. And yesterday we introduced the principle that lead to the operation of a gyroscope. So we have seen yesterday what is called a ring path of a laser gyroscope. So although yesterday we did this example in which we have a beam splitter here that is basically given by a mirror that reflect a part of the beam towards the anti-clockwise direction of this path, and the other part of so the other 50% of the beam is basically reflected by this mirror here and re-reflected by the mirror of the beam splitter that induce the clockwise direction of this beam. So we have two counterpart beam that are moving in the opposite directions. Yesterday I started with a simple example that we don't have any rotation of these structures. So this ring laser gyroscope is still. Of course, in space, you're not able to have something really still. You usually have rotation. This is only an academic example to show you what happens if, in principle, you're able to have something completely still. So if everything is still, we assumed that at the beam splitter you have also the detector. So the two beams are moving, one on the clockwise direction, the other one on the anti-clockwise direction, and they are going to move with a velocity that is equal to the speed of light. And since the detector is still, the two beams are going to have a path equal to 2 pi r, so the entire path of the ring. In this case, the two beams are going to approach with the same frequency at the detector. So when you want to, assuming that these two signals are with a different phase of half pi, when the two beams are going to interfere at the beam splitter, so at the detector, the two signals are going to cancel out. So you're going to have distraction interference. So you're not going to have any signal, because the two signals have exactly the same frequency, are opposite in phase with half pi, and you're not able to see any signal. The story is different if you have a rotation along the axis of the gyroscope. The axis of the gyroscope is orthogonal to the gyroscope itself. So if you have omega, it is indeed the omega of the omega of, for example, your spacecraft. Well, in this case, the detector when the two beams are going to leave the beam splitter, is going to move towards the clockwise direction. So when you do the sum of the path of the photon, so this is the path of the photon that is moving anti-clockwise, and this is the path of the beam splitter, so your detector. In this case, so with respect to the photon, so the photon is moving with the speed of light velocity. But you have to consider that the beam splitter is moving in the opposite direction of the anti-clockwise direction. So when the anti-clockwise beam is going to approach the beam splitter, is going to see it with a velocity that indeed is C plus R omega. So basically what it means is that it will see an increase in its frequency. So it is a classical Doppler effect, because we are treating this simplified description using classical physics. Of course, you should treat it using the relativity, so Einstein's relativity, because basically we are using light. But the classical physics is indeed a good approach to explain these the functionality of this gyroscope, because basically the two beams are going to approach a similar path. So this explanation by using classical physics is accurate enough. So give you the formulation that you need. So as I said, the sum of the two has to be equal to 2 pi r. So what I mean is that since the beam is going to approach the detector after 2 pi r, so the entire loop of the ring, this velocity here will be indeed C plus R omega. For the beam is moving in the clockwise direction, this beam is observing the detector moving away. So in this case, you have that is the velocity indeed is C minus R omega. So you are seeing a negative Doppler shift. So you're seeing that your beam splitter is moving away. So from these two, what we are going to measure is indeed the time at which the first beam, so this minus beam is approaching the beam splitter, and T plus is the time at which the beam splitter is going, the beam is going to approach the beam splitter. So you can see that this one will be larger than this T. By inverting these two expressions, we have found that T minus and T plus has these two expressions. So our purpose is indeed to determine the delta frequency for ring laser gyroscopes. So our goal, so for the ring laser gyroscope, what is usually done is measuring the delta frequency between the two beams that are moving on the contour part of the ring. So what we are going to do indeed is to measure delta Ni. But to do that, we need to first measure the optical path difference. The optical path difference is, as I said yesterday, given by the delta T that we have just measured times the speed of light. So if we use the expression of T minus and T plus, so this is T plus minus T plus T minus. So we are trying to measure the delta T at which the two beams are approaching the detector. As I said yesterday, C is definitely larger than R squared R omega. So you can approximate this expression to this 4 pi R squared. But so we know that 4 pi, so pi R squared is equal to the area of the ring. You can see that the delta T is directly proportional to the omega of the spacecraft. That is assuming in this case it is parallel to the orthogonal axis of the gyroscope, divided by the squares of the speed of light, the speed of light squared. So those are the fundamental equations of laser gyroscopes. We are assuming a circular path, but you can find similar expression also for other parts, like usually a rectangular or triangular path. The other thing is that for gyroscopes that are used, for example, on airplanes, you have also a medium in your path. So when you're trying to determine the velocity phase of your the phase velocity of your beam, you have to take into account the refractive index. Here we are assuming that they are moving in the vacuum, so that's the reason why it is a little bit simplified. But if you assume the refractive index, the basically conclusion that we are doing are exactly the same. Well, as I said, our main goal is to measure the delta frequency. So basically, when the two beams are approaching the detector here, we have to look at frequency fringes. So sorry, interference fringes. So basically, the two beams are going to have a constructed distractive interference, and we're going to measure, and this interference will be indeed related to the delta frequency of the two measurements, of the two beams. As we said, the delta frequency is given by the differences of the basically the Doppler shift given by the fact that the beam is moving towards the beam for the anti-clockwise beam and is moving away from the clockwise beam. So you have Ni minus minus Ni plus. This is the expression of the Doppler shift. You have a minus here because, as I said, you are seeing a negative frequency shift for the one that is moving. So for this one, if you explicit this form here, it is easy. I mean, you can easily demonstrate that this delta N is equal to the frequency of your signal, of your beam, times 2 times omega, so the velocity, the r of the ring gyroscope divided by the speed of light. We can do an additional trick by multiplying both side by 2 pi. So if you multiply by 2 pi both, it's a trick, actually 2 pi r, so your length of the loop. What you can find indeed is the expression that you have here. So this is 2 omega r c. So what you can see indeed is that you have here r squared. So you have a pi r squared, that is your area. This 2 pi r, as I said, is indeed the length of your loop. So at the end, an interesting formulation before arriving to this one is that your delta N, so the beating frequency, the differences between the two signals, is indeed equal to 4 times area of the ring times omega. So divided by, so you can multiply by C, ni time divided by C, L. This delta ni is your measurement, basically. So when you are going to, for ring laser gyroscope, because this is for laser gyroscopes in general, but for ring laser gyroscope, what it is measured in general is your delta ni. So when you measure the delta ni, you can see that this delta ni depends directly on the area of the ring laser gyroscope, the input rotation, that is your what you're trying to measure, divided by the length of the loop times ni divided by c. So this one is indeed so ni divided by c is your wavelength of your, so it is 1 over lambda. So it's the wavelength of your laser beam, okay? So it is a well-known property. So it is the beam that you are using to in the gyroscope. So A, L, and lambda are known parameters. The only unknown is omega. So if you are able to measure the delta ni of the two beams, you are able to determine omega. An important conclusion of these description of the instrument is that you have that in order to have a better estimation of omega, you have to increase the area of the ring. So in order to amplify the measurement, so for small rotation of omega, if you have a better knowledge of how omega is indeed varying, if you want to amplify this signal, and so you're able to measure your delta frequency, so the frequency, the beating frequency, what you can see is that you have to increase the area of the ring laser gyroscopes. So this is the main disadvantage, because of course in space you don't want to have large masses and large size of an instrument. The other thing is that you have limited length, because also if you want to increase the area, you have to increase the length. So for since you have the area is pi r squared, is in principle you want to increase that one, you're also going to increase L. Of course, it will be with so if you increase R, you're always able to increase the sensitivity of your instrument, but you have to be careful that increasing A means increasing the size of the gyroscope. The other possible formulation is indeed by substituting the expression of the optical path length in the delta ni. But of course, this is an additional formulation that you can take into account. When we are going to look at the fiber optic gyroscopes in the next lecture, is so the main difference is that the detector is not going to look at the delta frequency, but it's going to look at the delta phase. It will be really easy to demonstrate that the delta phase of the instruments can be easily determined by using the properties of the waves, in this case of the light beams. So let's have a break here, and we restart in 12 minutes to indeed conclude a part on the laser gyroscopes in general, but to focus on the ring laser gyroscope and the fiber optic gyroscopes. We have to conclude the laser gyroscope introduction, and we are going to see the two main gyroscopes that are used in space, but also in other applications, military, for aircraft, and we are going also to show what are the main differences between ring laser gyroscope and fiber optic gyroscopes. One of the main differences is already clear because, as I said, ring laser gyroscope usually deal with delta frequency. So we have a delta n that are given by those this expression here. When you want to deal with the fiber optic gyroscopes, you use usually delta phi. So you have to deal with delta phase of the two beam interference. Delta phi, as you know, is the delta omega times t. So you know that delta omega is related to the frequency, is the pulse rate. And you can write this expression simply by, so you know that delta omega is equal to omega times the optical path difference divided by the length of the path. So you can find by substituting directly, so this comes from that delta omega, so the pulse rate of your signal is given by omega times delta L divided by L. And you have that delta L is given by this expression here. So if you substitute this expression in this one, you can see that delta phi is equal to omega t times the angular velocity input of the spacecraft, the area of the ring laser gyroscope divided by LC. Why is important, this formulation? This formulation is important because the main thing that you have to point out when you are dealing with laser gyroscopes is that the delta phase, so the delta phase of the signal that is given by the interference between the two beams accumulates with time. So assuming that your gyroscope in this case is moving with an angular velocity that is constant angular velocity omega. What you have from here is that the delta frequency that you are going to observe is constant over time, and it is given by those parameters. The variation in phase is going to accumulate over time. So it's going to change and accumulate over time that is given by t. Why it is important that? Because, for example, for fiber optic gyroscopes, you're not going to look at the delta frequency, you're going to look at the delta phi by going to measure the interference fringes. So when you have, it is a similar concept when you have waves in a lake. So you have distracting and constructing waves, fringes that give you the amplification or the total distraction of the signal. So what you're going to see here is that if you're observing this phenomenon for a few seconds, the number of delta phi is going to increase. And also the number of fringes of interference. So let's see that you have these fringes here at time t1. At time t2, you will have a larger number of interference. And this is related to the time at which you're observing your signal. Since you know at what time you're seeing that, you are able to determine omega. So how the delta phi relates to the number of fringes? So those, the number of these fringes in a time t, for example, let's say that is t. a reference time that could be, for example, a time related to this is a time related to the interference signal. The number of fringes depends indeed by delta phi, and it is equal to delta phi times divided by 2 pi. So we know that if you want to determine the delta frequency, this one is equal to the time times delta n. The expression of delta n was determined before, and that it is, for example, this one. If you look at this one here, the only difference is that we substitute theta to be equal to omega t. So it means that since you are moving with an angular velocity that is constant, the angle of the spacecraft at which the spacecraft is as now is orientation is equal to the angular velocity of the spacecraft times the time. So with this expression here, you are able to determine the number of fringes that you have from a variation of your spacecraft attitude by angle theta. If you have a variation of angle theta of a certain amount, 1 degree or 2 degree, you know which is the amount of fringes that you can expect from your detector. You can also determine the number of fringes in a different way, because as I said, lambda is the wavelength of the beam that you know. It is a laser beam, so it is a property of the beam. The area is, and the L is the property of the ring laser gyroscope, or in this case, for a fiber optic gyroscope. So what you can see is indeed you can also write n as equal to the length of the path of the gyroscope divided by pi and lambda. The reason why you can also write this in this way is because, as you can notice, since the area is pi r squared and the length is 2 pi r, basically this one enables to explicit the number of fringes as the properties, the size of the gyroscope. So it means that if you want to have a larger number of fringes for a given theta, you have to increase your R. So it's the same principle that we have seen here. So here we have seen that if you have a specific property of the detector in the ring laser gyroscope that give you the minimum tolerance of delta n, you have to increase the area in order to have the possibility to measure tiny variation in the angular velocity. Same principle here. If the detector is not looking at the frequency, but is looking at your phase, and so the number of fringes of the interference, also this detector will have a minimum, so an N tolerance we can write. N tolerance means that you have a minimum number of fringes that you're able to measure from your detector. It means that if you want to measure tiny variation of the orientation of the spacecraft theta, you have to increase the size of your gyroscopes. That's the main problem of ring laser gyroscopes. So the fiber optic gyroscope indeed were implemented to overcome one of the main problems of the ring laser gyroscope. As you can see here, although those are called ring laser gyroscopes, usually have a square or rectangular or a triangular for a shape, and it is given by a certain number of mirrors that give you the path of, so in this case, you're not going to have that L is equal to 2 pi r, but you can indeed have, for example, that the L is equal to 4L, and you can determine the area as L squared. But the principle is the same. The main problem here is that the area and the area of the ring laser gyroscope represents the main important problem, because if you want to determine the a certain delta frequency or delta phase, if you have a phase detector, you need to have a larger gyroscope, a larger area, or a larger R, larger L. So the in this case is one of the side of this rectangle. So that's the reason why. But so you have also other problems with ring laser gyroscopes. So let me write another problem here. So you have other main problems with the ring laser gyroscopes. So first of all, what you can have, so in principle, what we have seen is that you can write your the trend between delta n as directly a function of omega. So this represents the ideal case, okay? This is the ideal case because you are able to okay, let me write with the text box because otherwise it will take a lot. What I would like to show you are a few problems that you have with the gyroscope. So let me, okay, so this is so another problem that you can have. So in the ideal case, what you have is that the at the omega equal to 0, the delta n that you are measuring is equal to 0. One problem that you can have, for example, so let me insert a text box here, and so this will be omega, and this will be delta n. Okay, so what you have here is that you're not going to have something that is going to pass through 0, but is going to pass close to 0. And this is called, let me insert another text box here. This is called non-zero null shift. So this one is given by the fact that you have a slight variation of the refracting index. So as I said, for ring laser gyroscope, sometimes you can have a medium. So, but these variations in the medium could also be given by of the refractive index could also be given by the mirrors itself. So what happened here is that at omega equal to a certain omega, you're not able to have any variation in your frequency. So this is given, as I said, to basically refractive refractive index issues. The other main problem the main problem of the ring laser gyroscope is called the lock-in problem. So the lock-in problem is similar to this one. So, but you have that in this case, the dashed line will be the ideal case. In this case, so for the lock-in problem, you have something going like that. This is an important problem because it means that for low omega, you are not able to have any signal for the delta frequency. So you're not able to measure low omega. This is called lock-in problem, lock-in issue. Oh, frequency locking. So that will be it would be almost the same. So so what happened here is that basically the two beams that are moving counterpart are going to lock in a way that although you are seeing an omega so the detector is moving with a certain omega, the two beams tend to be at the same frequency at the detector. So there is a mechanism that basically tends to provide the same beam frequency at the detector for small omega. This represents a main problem, and one of the main solutions for this lock-in problem is to, for example, provide a different polarization between the two beams. That's the reason why, for example, here you can find anode and cathode. So basically, these anode and cathode provides an electric field in order to provide the Faraday effect that enables the polarization of the beams in order to determine the a slightly different polarization in order to avoid these lock-in problems. However, this works only if you are looking at delta frequency. If you are looking at delta phase, this problem doesn't work. So another solution for this problem is called dithering. So introduction of noise. The introduction of noise to basically avoid that these small omega cannot be measured. So this dithering can be done, for example, by oscillating the gyroscope in order to provide an omega larger than the one that you are measuring, but with an average that is going to not bias your solution. However, those are not really important heat issues for us, because the problem is that the dithering, for example, is not very useful in space because you want to avoid the movable parts. So one of the solution that was so one of the alternative configuration of the laser gyroscope are the fiber optic gyroscopes. The fiber optic gyroscopes are indeed the possibility to avoid these issues that I have slightly discussed here, but also to solve one of the major issues of the ring laser gyroscopes. The big issue that we had is that if we want to increase the sensitivity of our measurements, we have to increase the area. Well, the solution of the fiber optic gyroscopes is very, very easy, because basically it takes advantage of the fiber optic coil. So basically what happened is that the fiber optic is going to provide a number of loops that would indirectly increase the area that you are going to measure. So what happened here basically is that assuming that you're still having a ring like this one, but since you have different coils basically that are turned around in this path, what happens is that the two beams are going to basically go within this path multiple times, let's say n, with n the number of coils. And so you are indirectly increasing the area of your gyroscope. How you are increasing the area? So if we retake the description of the time differences between the anti-clockwise and the clockwise direction, the clockwise beams, you have now in front of 2 pi r, so the length of the path, and n, that is the number of coils. If you do the delta t, so the same exact formulation that we have seen before, what you can see that the optical path at the end will not be only 4a omega c, but will be increased by the number of coils. So this is not the refractive index, this is the number of coils. Do not be confused with what we have seen before with n. So what happened here, as I said, fiber optic gyroscope are going to look at the number of fringes that is given by delta phi divided by 2 pi. This one for the one that we've seen before. So if you have only one coil, what you have here is that is directly proportional to the area of the gyroscopes. But including a number of coils, you are able to increase directly with the same area the sensitivity of your instrument. So at the same theta, you are able to have a larger number of fringes because you have a larger number of coils. So the main principle is that since the fiber optic gyroscope, the fiber optic do not have a significant mass, you can indeed have fiber optic length of several kilometers that are basically put around an area of a very small area. And so you can design a gyroscope with the same sensitivity of a ring laser gyroscope with a very limited area, or by using the same area with a definitely higher resolution of your instrument. If you want to do a simple exercise, we gave you some numbers here. For example, a characteristic equation of the gyroscopes could be 10 centimeters. And so you are able to, by using, for example, an angular variation of 0.1 degree per hour, you are able to determine which is the number of fringes that you have in case of a fiber optic gyroscope or in case of a ring laser gyroscope. So the main advantage of a fiber optic gyroscope is indeed the fact that you are able to have a much more compact design of the gyroscopes. The other main advantage is that those gyroscopes are not affected by the lock-in issue. So what you have here is that since the fiber optic gyroscope are looking at phases, you are not able to have this lock-in problem that is indeed related to the delta frequency. So what you have to take into account here that, as we have said for the link laser gyroscope, you try to induce a different polarization between the beams in order to avoid, for example, the lock-in effect. Since here we are looking at phases, you don't need to induce any different polarization. But actually, since you're looking at the delta phi, so you're looking at the number of fringes in your interference wavelet, you need to have the exact same polarization between the two beams. So the difference between the ring laser gyroscope and the fiber optic gyroscope is also that you have a polarizer before the beam splitter. So the two beams are at the exact polarization, and that will be clear when we are going to discuss how the number of fringes are computed for the fiber optic gyroscopes. So you have to be careful that also this is one of the main differences. So the main advantage of fiber optic gyroscope is indeed they are small, compact, and you can indeed provide a three-dimensional instrument by placing this instrument in this box like this one, or for example in this shape here. So the advantage is that the tiny shape, the tiny mass that you need for a fiber optic gyroscope, you are able to have this much more compact design of the instrument. So here briefly, we want to discuss how the number of fringes are computed, because we have said, okay, so we know that if we have a variation in the angle, an angular variation of the spacecraft attitude, we are able to measure a number of fringes. But how those fringes are computed in the sensor detector? Well, what it is computed indeed is the irradiance of the signal. So since the two signals are at the same polarization, you are able to check the intensity or the irradiance of the signal itself. So the interference signal that you have, so the intensity of the signal is given by the sum of E1 and E2. And we show you, for example, this complex formulation where omega-1 is the frequency of the signal, for example, the clockwise, and this one is the anti-clockwise. And phi1 is the difference in phase. This is for a generic wave. So assume, for example, that between phi1 and phi2, you have a difference, a delta phi of so are basically are opposite in phase, so they have a phase difference, a delta phi equal to half pi. That means that if you have omega-1 and omega-2 equals, so you don't have any variation of the orientation of the spacecraft, when the two signals are going to the detector, what you get is indeed that the signal is going to cancel out. So the intensity of the signal is going to be 0. But to compute the intensity of the signal itself, so these are the so the intensity is given by the integral of these vectors of E1 and E2 that we have defined here. So the intensity, the irradiance, is indeed given by the integral over a time span that could be, for example, few periods of the interfering waves. So don't be scared about this formulation. This is indeed a general representation of the intensity of two waves that are indeed going to interfere at the detector. So what you have at the end, this intensity can be written. So this integral, since we know that the variation of the cosine term is slowly varying with time with respect to this period t, we have that this intensity, it will be given by the amplitude of the first signal plus the amplitude of the, so the intensity of the second signal, plus the dot product of E1, E2, and the cosine term of delta omega and delta phi. So here I reported a simple case in which, as I said, for example, omega 1 and omega 2 are equal. So you have the delta omega is equal to 0. So what you're going to see is that what happens in case you have the delta omega is equal to 0 and you have only a phase difference, okay? What happened here is indeed that when you have the delta phi is equal to half pi, you have that the red signal that represents our I is going to cancel out, okay? In principle, what we are going to measure is that delta phi is assigned by the beam splitter. So we know the delta phi, how it is. The only phi is going to change is the delta phi. So the delta phi is induced by the omega. So it is proportional to omega, big omega. So the intensity will vary with two. So if we assume that the two signals have the same intensity, E1 equal to E2, we assume that these two signals are indeed going to give you an interfering beam that oscillates between 4 times the intensity of the single beam and 0. So if you count the number of zeros of this intensity, you're able to measure your n. Your n is given you the number of zeros or the number of maximum signal. That is important because, of course, give you the what we have discussed here. So so this explains how the sensor work. So you know that you have a number of zeros that is given by this intensity function, and from this one you are able to determine indeed from the number of you know that this one is proportional to theta. That is the angle at which the spacecraft is moved with the time t. Okay, because we know that theta is equal to omega t. So if you want to assume, if you want to have an idea of that, how does it work, assume that here, for example, what happens is that so if green is the anti-clockwise and the blue is the clockwise, the green, it is the anti-clockwise, so you will have a larger frequency, so you will have a larger frequency signal, and the blue one will be with a shorter frequency, so will be with a larger wavelength. When you're going to build this red signal, you're going to see that you're going to have an expression that is similar to this one. And so by counting the number of zeros for a specific time t, big T, uppercase T, you're able to determine the how the attitude evolves. So to conclude that, because I would like to also introduce the resonating gyroscopes, I took from YouTube this video from the LD didactic that show you how the gyroscope works. So basically, it is the ring laser gyroscopes with the triangular shape that show you, for example, how the two signal varies over time. So the fact that we've said that they changes their frequency, And so you're able to see how the frequency of the signal changes over time because of the variation of the angular rotation of this gyroscope. And also at the end of the video, you can see that this one, you're able to see the same measurement in terms of phase shift. So what we have seen so far, so the interference fringes. So the fact that when you have angular variation, very so a spin rate that is constant, you're going to see that the fringes are going to accumulate over time. You see that they are going to accumulate over time, and by measuring these fringes of interference, you are able to determine the omega, the big omega. So we have only 5 minutes, so tomorrow we will start with this one. But as I said, the other main gyroscope that have been used in actually in space are the hemispherical resonating gyroscope. So we are not going to discuss that in big details because it's not really needed. But what you have to keep in mind is that these hemispherical resonating gyroscopes are indeed based on a mechanical principle. So are not based as a laser gyroscope on the Sagnac effect, but it actually are based on the fact that a wine glass shape body in vibration will keep inertial properties that are stable over time. And so you can indeed use these properties to have a reference frame that give you information on the angular variation of the object. So to show you in briefly what is the concept of this resonating gyroscope, I will conclude with these. So the original principle that gave the idea to this gyroscope. So in the 1990s, this physicist Brian of Peter's College noticed that if you have one glass that, so by beating a white, he struck basically a wine glass, he saw that this vibration, so the vibrational mode of these glasses behaved in a specific way. So basically what he discovered in his experiment is that by basically beating these wine glass, the vibration, so they're induced on the wine glass, create a continuous tone. This continuous tone, however, is not the same if the glasses is basically put in rotation around the stem. So if you rotate the glasses after, so he struck the glasses in order to induce this continuous tone, and he started to move to rotate the glass around the axis that is parallel to the stem. The stem is this one. So by rotating these glasses around the stem, he noticed that the vibrational mode, so the behavior of the glass followed specific patterns that were related indeed to the angular velocity of the at which the wine glass was perturbed. So the main important thing is that what we're going to see is that the Coriolis forces that are acting on the vibrational mode of the glass induce a specific precession of the vibration patterns of the glasses that are directly related to the rotation omega at which the glass is rotated. So basically, it means that if you vibrate, if you put in vibration an object with this shape, you are able to determine, and you start to rotate this object, you are able to determine the angular variation of this object. So basically, the main mechanical principle at which this object is based on is indeed the effect due to the Coriolis acceleration that are acting on the rim. So you have that this object is rotating, and the Coriolis acceleration acting on the rim creates a different patterns of vibration that are directly related to omega. So it sounds to be weird that from an experiment based on a wine glass could be relevant for space, but actually this important discovery that was done in 1890s was completely ignored for many years until 1965, when they started to rethink about the possibility of use this property of resonating hemispherical object to determine indeed the angular variation, and so to use this principle for gyroscopes. For other 20 years, there were a lot of improvements into the technologies, and only in the 1980s, this technology, so by using a shape like this one that you can see here, it reminds indeed a wine glass. So by putting vibration, this object, you're able to have an instrument that give you very stable measurement of the angular rotation of, in case you apply this gyroscope to an airplane, or if you apply it to a spacecraft, So the main advantage of these hemispherical resonating gyroscope in the last 20 years were basically represented the main gyroscope used in space are that are small, as you can see here. Basically is the size of a coin. Low noise, and that's one of the other main properties that we're going to see also tomorrow, because we're going to model the errors of the gyroscope, and high performances. So tomorrow we are going to conclude this part by explaining a little bit better the principle that is behind these hemispherical resonating gyroscope. We're not going to quantify exactly, for example, how the angular velocity is associated to a variation in the vibrational mode. That would require a separate course. But we're going to show, for example, the characteristic of the sensor. And tomorrow we'll conclude the part of the gyroscopes by discussing the model error of the gyroscope. That is really important and fundamental for the modeling of the gyroscopes. Okay, so